Hello class, welcome to our second half of section 7.3. This is again estimating the population mean. So we're finding confidence intervals dealing with means and standard deviations. However, in this scenario and in today's lesson, sigma, the standard deviation of the population, is unknown. So everything we've done up to this point has used the z-score table, but because standard deviation is unknown, it's going to adjust what we can do just slightly. We're going to have to use what's known as the t-distribution table. Now that's been posted online. It looks a little bit different. Okay, that document, that table, has a couple different pieces that we want to look at. It's also in your textbook. So my suggestion as we're going through today's lesson is that you're looking at that table. Notice here that the critical value, or like finding the z-score, is found in a very similar fashion as finding the z-score, the t-table. So this is x bar still, which is the mean, minus the standard, or minus the mean of the population, divided by s now instead of sigma, because we don't know the standard deviation of the population, but we should know the standard deviation of the sample, divided by root n. So really this formula is exactly the same. It's just going to change slightly because we're not going to be as confident about what we can do on these situations because we don't know the standard deviation of the population. The other important thing about this standard deviation when it's unknown is that to use the t-table, you have to use what are known as degrees of freedom. Degrees of freedom basically can say, like, what types of restrictions do we have, how many options do I have, what types of issues am I going to run into on this data set. And so the degrees of freedom for our situation is going to be n minus 1. And basically what that says is we're a little bit less confident than we should be long term. And so we have to kind of get rid of a little bit to give ourselves a little bit more value on both sides of the confidence interval. And so after we impose all of these restrictions, we're saying there's n minus 1 that's available. And so the degrees of freedom, which is denoted df in your textbook and in the notes, will always be n minus 1 when using the t-distribution table. So finding critical values. So the first thing is to make sure that you're looking at your table. So sample size is 7, and the distribution of the population is normally distributed. That's still going to be important. You want to make sure that n is at least 30, or the standard deviation idea. So that idea still is useful. But to find the critical value, t alpha over 2, corresponding to 95% confidence. The important thing for your table is, first off, you got to use the t-table. The degrees of freedom would be 7 minus 1, which is 6. Now, this is a two-sided test. Okay, so if you look at the top, it says area in one tail and area in two tails. This one is two-tailed because the 95% confidence says here's the middle 95%, and what's left over, okay, should be half on each side. That's where the alpha divided by 2 comes into play, which means it's 0.025 on the top and bottom, these small areas here, with 95% in the middle. So when we're looking at those situations, that's kind of what we want to find. So you got this 2%, 2.5% kind of in the middle, and then the leftovers on the two sides. When we're dealing with that situation, okay, the t-table, you go to area of two tails, 0.05 with 6 degrees of freedom, and your t critical value would be 2.447. Notice that this is a little bit larger than the z critical value that would have been for 95% confidence of 1.96. So really the t-distribution is just going to be slightly larger, okay, and expand our confidence intervals because we're not as confident because we have this degrees of freedom idea and we don't know the standard deviation of the population. Okay, the degrees of freedom, if you look on the left side, they kind of go by ones for a long time until you get to around 40, and then it kind of goes by fives, and then by tens, and then by hundreds. I think it's probably better to round down for your degrees of freedom if it's not in there. So for example, if 82 is the degrees of freedom, I would use 80. Your book tends to go to the closest one. So if you notice that you're off by a little bit, just go to the closest one and that might solve your issue. A lot of times it's the same, and so it won't be as big of a problem on some of these scenarios. I think it's better to round down though, because you want to make sure you include enough to make it work. I mean, the numbers are going to be so small, the incremental difference is probably negligible in most cases. But if you notice that something's up, just round to the closest instead of rounding down. But I think in good conscience and in good kind of good ideas for this type of scenario, it would be better to round down in these types of questions, and I would count kind of either situation correct. Okay, the confidence interval, this should look similar to what we did before. So before it was always the z-score times the standard deviation divided by root n. Well, now it's the t score essentially, or the critical value from the t table, times s, which is the standard deviation of the sample divided by root n. And then the confidence interval is found the exact same way. The sample mean plus or minus the margin of error. Your requirements still are in play, so either it's a normal distribution or n is at least 30. Okay, so n has to be greater than 30 at that point. But these two ideas are very similar to the z-score formula. So if you notice that you keep getting answers kind of close but not quite correct, it's probably because you're using the z-table instead of the t-table idea in order to figure out when standard deviation is unknown. Okay, here we go. Construct a 99% confidence interval. Okay, this says n is 9, x bar, the sample mean is 75, and sigma is 15. Now, if they give you sigma, the standard deviation of the population, that's automatically a z-score question, and that should be one of the easy ones from your z-score table. So z should be 2.575. This is a normal situation with sigma known. So the margin of error, 2.575 times the standard deviation of 15 divided by root 9, and I should get 12.875. The confidence interval then is 75 plus or minus that 12 number, which becomes this final answer down here, the 62 up to the 87. A lot of students are rounding these numbers too far. If you're trying to round to the nearest hundredth, for example, on the final answer, go to 3 places as you go through. The homework will tell you what to round to. I'll tend to go 2 or 3 places on my questions as well. When you're finding z-score ones, they should be the nice ones from your table. From the bottom corner that deal with confidence levels and confidence intervals. But again, we use the z-score table here because we knew sigma. The next question says that n is 75, x bar, the mean is 98.6, and then s equals 0.6. So first thing is, that's standard deviation of the sample, which means it's t-distribution. It says the population has a skewed distribution, which could be a problem, but it's okay because n's greater than 30. All right, so let's go back to this s equals 0.6. Degrees of freedom is 74 because it's 75 minus 1. This area is 0.01 because it's a 99% confidence interval. If I'm looking for a 99% confidence interval, that's a two-tailed test with area is 0.01 because 99% is on the inside and 0.01 collectively on the outside. Remember, that's two-sided because the confidence interval shows the middle 99%, and so there's 1% left over. I go to 74. I would round that down, okay, to 70, which the t in the t table will be 2.648. Make sure you're looking at a t table to find that number. Part of what you're going to have to do for this section and with your homework is to find that. So you want to make sure that you're able to figure out how to find that answer in your t distribution table. The margin of error then is the t distribution piece that we just found times the standard deviation divided by square root of n. I multiply that through and then add and subtract it from the sample mean, which is the 98.6, and then this would be your confidence interval up to 99%. Okay, when you're looking at those situations, you want to make sure that you're finding the margin of error, okay, using the t-distribution table, and then using that to help find your answer. One note here, when I was writing, I think I may have misplaced and put a 5 here instead of an 8, so you want to make sure you adjust that slightly. That will only slightly adjust the margin of error, so you just want to make a note of that should be an 8 right here, and then the margin of error would be slightly changed based upon that information, just so you're aware. I think I must have been thinking of 575, and I probably just wrote the 5 there. So make sure you use this 648 number, not the 575 or the 645. Okay, this next question has a lot of words, so when you have a big question like this, we just need to make sure we take out the important information. So for example, this says the common claim is garlic lowers cholesterol levels. In a test of the effectiveness, 49 subjects, that's N, are tested with the dose of raw garlic. Cholesterol levels were measured. The changes in their level have a mean of 0.4, so that's X bar, that's the sample mean, and a standard deviation of 21. Now, it says the changes in their levels, so that's the sample standard deviation, so that's S. The degrees of freedom is 48 because if N is 49 minus 1 would be 48. Double check that you can find this t critical value. Okay, it's a 95% confidence, which means I want 5% to be the leftovers. And then plug that in for your confidence interval. So you have to find the margin of error using this t-distribution table information. So this t-score, or this t number goes in for 2.014 times the standard deviation of 21 divided by root 49, and I get just above 6.042. The 95% confidence interval would be 0.4, the sample means, plus or minus the 6.042. When I find that answer, I get a negative to a positive. Okay, so negative 5.6 to positive 6.4. That's okay in this situation because what does X bar represent? This is the average change in their cholesterol level. So when we're looking at this, what this is saying is I'm 95% confident that the actual the actual change, net change in cholesterol level is between negative 5.6 and 6.4. What this tells us is that we can't really say the garlic is effective because the confidence interval has some negative and some positive numbers, which means I don't know if it's going to actually help or hurt. It's somewhere in that range. If the entire confidence interval was negative, then I would be fairly confident that it does lower my cholesterol level because everything would be a mean change of a negative. If all the numbers were positive, I would be fairly confident that it would raise your cholesterol level. But this one doesn't give me much confidence at all because 0 is included and everything else is in between also there. What's really happening here is there must be some other reason that your cholesterol level goes up and down. So there's probably some effect of the diet that you have with the raw garlic. And maybe it's the food you're eating with the garlic, not just the garlic. And so when you're looking at a situation like this, that might be what's happening here. So again, if the confidence interval, this would be the same for majority. So majority would all have to be above 0.5 or below 0.5 to say anything about the majority. If the number that you care about, so this mean change, everything should be negative if I want to show it's effective. If any slight part is positive in this confidence interval, I can't make any valid conclusion. This takes time and practice in order to see some of those things, so that's something that you want to look at. One other suggestion for your homework is you might have a data set. If you're given a data set, they may not give you that mean and standard deviation like I did in this question. You're going to have to do one var stat or summary stats. Stat, summary stats, and then one variable, and run that through a stat crunch for your homework, and that should find the mean and standard deviation for you. But you may have to do that in those situations. In testing situations, we have to be a little bit more creative and maybe giving you that information just because of time purposes and the fact that you wouldn't have necessarily StatCrunch to look at for some of those questions. So just things to keep in mind as you move forward on your class and in your test situations and your homework. Remember, anytime that you have S, not sigma, standard deviation of the sample versus standard deviation of the population, you have to make sure that you use the t-distribution table, not the z-table. If you're given sigma, the standard deviation of the population, then by all means use the z-table. Part of the issue on your testing situations is you have to recognize which version you're using at different times. So make sure you're paying attention to that. Make sure you start reading your z-table and reading your t-tables appropriately. And for now, the t-table, you can probably just look at area of 2 tails. When we get to chapter 8, we'll look at the area of 1 tail a little bit closer. Have a good day, everyone.